before we draw our first graph, and before we draw our first graph, let's take one of them and linearize it, right? So we have to be able to, regardless of what form they give us, we have to be able to linearize, right? You might remember what linearization is. Linearization is putting it in the form y is equal to mx plus c. All right? So let's start with the first one. Let's start with example 1, because we're not sure which of the formulas they're going to give us, because there are many variations of those 3 there, right? So let's say they gave us something like this. Let's say they gave us f on the y versus vs on the x. And we get something like this, right? The question is normally be, okay, well, plot v versus vs. And then find what's the gradient, find what's the y-intercept, and so on, right? So let's use the equation with f and vs in it. Let's start here. You remember the concept? What's the concept again? Linearization, right? Putting it in the form y is equal to mx plus c, right? This is your y. This is your x. This is your m. And this is your c. Right? So let's see if we can linearize this. Someone every time, someone every chair. Copy them until right here, and then we'll do together. If you remember what to do, go right ahead. We'll only plot one graph, so make sure you get one graph each, right? Yeah, now. Supposed to wait. Graph paper. Yeah. Ready? So let's go. So we have to put it in the form y is, huh? Too bad. We had to put it in the form y is mx plus c, right? So you want to make f the subject. So the first thing you want to do, because f is y, right? Divide by h. So when I divide here by h, I'll get f. When I divide here by h, I'll get f naught. When I divide here by h, I'll get e on h. And we're good to go. If I rearrange this, I'll get f is equal to e on h vs plus f naught. What this is? This is the quantity on the y. This is the quantity on the x. This is your gradient. This whole thing here is your gradient. And this is your y-intercept. So if the question turns out to be f versus stop potential, your gradient is e on h, your y-intercept is f naught. Okay? So if I said from the graph, Shazana, if I said from the graph, find h, what you'll do? Find the gradient and plug it E and find pH. E is what again? E is the charge of an electron, right? Okay. So you have different versions. Try this one here. 1 on lambda versus Vs. Try number 2 there. I remember the answer. That is what I'm doing. I'm sure a lot. Oh, yep. Linearize this one here. Take your time and linearize it, right? Right? All I want to know is what is the gradient and what is the y-intercept. Alright, let's go here. Right, I give you a simple one just to start to do, right? We're just doing one alone. I just want to wrap up this photoelectric effect from last. Right, you'll linearize this one here. So it's 1 on lambda versus Vs. So we start with equation 3. C on lambda is equal to C on lambda naught plus EVS. We can divide throughout by HC. So you'll get 1 on lambda is 1 on lambda naught plus E on HC Vs. This is your Y. This is your C. This whole thing here is a gradient. This is your X. Right? Remember what E is, right? E is the charge of an electron. What is C? 3.0 by 10 to the 8. Right? 3 by 10 to the 8, right? Speed of light. Okay? And then there's normally ask you to find H something. But you know what H is, right? So you know what you're supposed to get. Okay? So these two examples with these graphs, right? Take a read there. Take a read of the one on board. Sorry, on the screen there. So the one I want us to do in class is they give you a wavelength in what? What is wavelength in there? Nanometers. Nanometers. Right? Nanometers. Convert your wavelength into frequency. Use the stopping potential, plot the graph, and then work it out, right? But before you do anything, what's the graph you're gonna plot? What's the graph you're gonna plot? Vs versus F. So it's a reverse of this. So before you do anything, just linearize it, please. Linearize, copy down that table, and let's work it out. Right? Yeah, and they say Vs versus frequency. Vs on the Y. So you had to rearrange the other way around. The one they gave you is Vs on the Y, F on the X. Right? So you had to rearrange some things here. Alright, copy it down. Let's linearize. Right, linearize this in my first, please. Before you jump into the graph. Please look above what they ask you to plot, yeah? Right, please look over what they ask you to plot. They ask you to plot. They ask you to plot stopping potential versus frequency. Yeah.
But if plot the graph based on that and balance the table,
No, you pass on the table, you use wavelength. How you find frequency if you have wavelength? Think of the formula relating lambda and b.
so you
That's not. I'm going back to my first question. The graph that we have to plot. The graph that we have to plot is stopping potential versus frequency. Right? That's the graph we have to plot. So I want you to linearize the first formula I gave you. So you know what the gradient and the y-intercept. Right, next. If you have frequency, if you want to find frequency and you have wavelength, how are you doing that? What's the formula linking both of them? F is equal to yes. You're using the formula V is equal to F lambda. Right? And V is the speed of light. So you're using F is equal to C on lambda. Right? Do that please. Find all the values and plots. But linearize the plot. Just many time. Right? That's my values now. What you all got for the second value? 5, 6, stick with the same number decimal places, right? 5.05. What's the next one? 4.90. Right. And now for the graph. You all linearized already? Right, remember you're using this same one here. What you want to make it subject again? You're gonna make VS the subject, right? So you rearrange it, you put your EVS here, and you move this here. You'll get HF minus HF naught. And then what you will do? Divided by E. So you'll get VS is HEF minus HEF naught. Right, online? Click on the little camera, right? And so VS is your y-axis, F is your x, H on E is your gradient, and this is your y-intercept. Yeah. All right? Plot the graph, and then look here. Watch underneath, right? The way you find H. Oh yeah. Plot the graph and the way to find H from the graph. Yes. Yeah. Yeah. Not your graph online, you can try to work out. You have two things to work out, right? You have to work out Planck constant and the work function. Yeah, going back just now. Right online, you're doing Planck's constant and the work function. So you need your gradient. What do you need? You need the gradient and your y-intercept to get Planck constant, right? Yeah, plot the graph. What's a good scale? On the y-axis, looking like 0.05 something. On the y-axis, 0.05. Right, 0.05. On the x-axis, do not break it up. Do not break the x-axis because we need the y-intercept. If you break your axis, your y-intercept will be wrong. Do not break your y-axis. Do not break your y-axis at all.
Yeah, you that's so small, right? People radiations. I don't know.
Yeah. Well, if you do start it, you can also do it like this together, you want to start it, right? I don't know.
So, we're not asking about all. People don't talk about those sort of, I told her, something like that, just. Yeah, probably, but the two. What's the last thing? You said last thing. Yeah. All you use was. Yeah, and about we. Yes.
That's okay, if it's not enough, we're ready, don't worry, if you didn't turn the page.
And maybe the.
Point.
Or even what else? No, okay. Still not that it's not. No, it's even.
Oh, yeah, you can get in one graph, that's not great.
But this trouble, when it's just easy. But now it's pretty all the version. So you can scale it up. So. Nobody is one. I don't know. I don't. Guidance so I say. Guidance so I say. Guidance so I say. Guy in front of me. You want it up? Oh. We got to show how to. Because I. Oh, guy.
Oh yeah, plot the graph, get a y-intercept, let's see what she got, right? I'll borrow somebody graph and work with it. Online, anybody finish plot the graph? Can I pick from an item? Can I finish it? Write down the graph. Right, you will know it again, right? Because you know the value for each. What I mean.
Yes, we should have. I feel like I said that. The best for him. I didn't have to. You know, I don't think it, but. The fact that I use share by.
Yeah, find the best line plus correct. So from what we see in the graph should have really looked like this. I see a graph might have looked something like that.
Yeah. Find something like it. And I feel like even if I did it correctly, like this is fine, everyone else knows it's. Yeah. Yeah, but. This. Well, small. Yeah, something else.
Find the gradient cell, find the gradient cell. See how good it tell you get best fit line and let's see how close to each other we get. So I told you we down and we'll use the x-axis, we'll use the x-intercept. Find best fit line still and we'll use the x-intercept. So 3 points. All the points can align. So use the points and numbers. Use the points. Points can actual sum. If they were more spread out, then make it so. Pick 2 points, find the gradient. But right, so I just want 2 things. Anybody online got the gradient as yet?
Yeah.
I want the gradient, tell me what you get, and tell me what you get for your y-intercept. Well, yeah, just one thing. When you read off your frequency values, please remember to write 10 to the 14. Huh? When you remember the f value, say divided by 10 to the 14. So every frequency value you read off, you gotta put 10 to the 14. Hurry up. Any answers to gradient online?
Get something minus 50, minus 5, without. Like, I don't even know my calculation. That's what based on what we have here, and we love this value. 4.5? Yeah, yeah.
Anybody got those values? 4.5 by 10 to the 14. And gradient I have here 3.5 by 10 to the minus 15. Come on, anybody got that?
Yeah. Oh, yes.
Wait, what you got this gradient?
1 point.
1 point? What you got? 14 or 15? Katrina, anybody online? You all got that value for gradient? Somewhere you gonna please. Should be 15, might be 15, minus 15. I don't know how. No, I just gonna go here. Read off your work function value as well, right? I am going to work with those two for now. All right, so by now you should reach here. All right, so after you have this here, if you come back here and you check your gradient, right? Your gradient is equal to H. Your gradient is H on E. So it means that H is a gradient by E. So multiply your gradient 6.5 by whatever you got. Multiply your gradient by 1.6 by 10 to the minus 19. Some more you get. Right? So use this here, use this value here to help you find your H. I lost it. You might again. You use your value, Shilana. Now let's see who got closer to the actual thing. How much you got here? 5.6.
Yeah, by 30 minutes.
Right? By 10 to the minus 34. Right? Well, you should remember your SI unit, right? Joules per second. How much you got, Shilana? Right, so should be around 34. Right? Well, yours was minus what? Minus 15. Oh, your value a little off, but right. So if we know the work, if we know this F0 value, Jacob, how we get work function? If we know F0 from the graph, because we could have found F0, we could not get a y-intercept because of how we initially plotted, right? What's the work function? H by F0, right? So you multiply H by F0. Right? The bad thing is that you might have to use your H value here. Right? You'll have to use your H value here. So that's 5.6 by 10 to the minus 34 by F0. Because we do have a y-intercept, we had to do this. But if we got the y-intercept, we just have to we would have gotten it here. If you got your y-intercept, you would have gotten minus hs naught on e. And just get rid of the e and it done. How much is this?
Point five two by 10 minutes,
2.5
2 by 10 minutes, 47.
minus 0.9. Check it out. This is positive 40.
Oh, yeah, sorry. Minus 32. But the value is wrong. It's 1.134.
Check it back one more time. I'm using your two values, right?
Yeah, it was just 2 minus that, but it's 40.
Right. Fix that back for now.
So 1.134 by 10 to the minus 3.
32.
134 by 10 to the minus 3.
This is should be around 20.
And over.
Check it back and make sure you put it in. That's only graph quick now.
Okay. Do my 10 to the minus 93.
Right, that makes sense. 2 points.
5 2 by 10 to the minus 90.
Right, remember is it should be close to these values and choose, right? It should be close to the minus 90. All right. You'll take forever with our graph, right? Let's take a look at the next topic. You're looking at this, look at my phone, look at that. Look at your phone. I know what's anything to know. All right. So let's move on. So the next thing we're looking at, take a look at the handout. Next thing we're moving on is to something called the wave particle duality of light. Right, learn this little summary here, right? Learn this little summary here. It gives all definitions of things that we did in the last 2 weeks, right? All right, that's at the end of the handout. All right, so let's take a look at something called wave-particle duality. What you think this means? Wait, what do you think wave-particle duality means? Light having both wave and particle properties, right? So let's take a look at what this guy said. So to explain some aspects of light, Mark, watch up here now, right? To explain how some aspects of light behavior, such as diffraction and interference, light is described as having wave properties. But, well, listening, take up. But for aspects such as the photoelectric effect, we describe light as having particle properties. Okay? So we are going to take a look at where this wave particle duality could also be proven. We saw it where first? Here, right? Photoelectric effect. So we saw the introduction of the particle behavior of light. Now, a guy named De Broglie could go and show us the same thing. Right now, his name is spelled is look like what it is. It's look like this, De Broglie. But now it's very Broglie. The DI, the D is silent. Broglie. I just said De Broglie. Right? I just said De Broglie because everything is, letters there, right? But the DI is silent. All right. That's the language that where the guy come from here. DE. So it's very Broglie here. It's French? All right, so let me take a look at this here. Where was I? Right, so we describe light as having particle properties. Therefore, light exhibits wave-particle duality, both wave and particle. So what we're moving on to, right? What we're moving on to is that every single thing around us has light and particle properties. If you all look at a football,
You need wave and particle.
wave and particle, sorry. If you all look at a football, that's not waiting on China to finish it. I waiting on China to finish self-feed the story that she messaged to back to China. Ready? Right, so watch here. Right, so to explain the aspects of light, we talk about that, right? So now we're going to take a look at particles like a football that has particle properties, obviously, but it also has wave properties, right? Every single thing around us has both wave and particle properties, but one is more prominent than the next. All right? So wave particle duality is not confined to light only. Every object exhibits particle and wave duality. All objects, from electrons to footballs, right? All of those have particle and wave properties. Right? But again, what do you expect to see more in a football? Faith. What do you expect to see more in a football? Particle properties or wave properties? Particle, right? But it also has wave properties. The behavior of relatively large objects is dominated by particle behavior, although they exhibit wave, and the reverse is also true. Right? There was a guy named Broglie, right? And here's what he was able to show. In 1923, Louis de Broglie predicted that since light exhibited both wave and particle behavior, particles should also have both wave and particle behavior. So what you see? Actually, let me show you on board. So we are going to show this relationship here. Lambda is equal to H on P. All right, so watch this here. P is movement. What? Yeah, but
Some city anything, no, but you gave me that send.
All right, so what's here? E is equal to MC squared, right? So we also know, and the entire proof here, so you don't have to write it, right? We also know that E is equal to HF, right? Excuse Faith and Jacob for your listening, right? What we can do after that, Olio, since we know those two things there, what we can do after? Make them equal, right? So we could say that HF is equal to MC squared. Can we cancel anything opposite? No. What do we know F is again? F is what? C on lambda, right? So what would happen here? HC on lambda. So one of these C's will cancel. Are you okay with that? Yeah? So what would happen if I move M across? If I move the M across, I will get C, which is speed, is equal to H over M lambda. And if I rearrange, right? Hold on, I rearrange bargain. Right? Let me just carry across lambda. I'll get MC lambda is equal to H. So I'll get lambda is equal to H over MC. What is mass by speed? What is mass by velocity? Momentum. So wavelength is equal to H over P. That formula there, that formula that you see in there, is called the Broglie's wavelength. Right? So what you see, right? Wavelength is a what property? Particle or wave? And mass. Mass is a what? So what we see in here is light having a wave property, which is wavelength, and a mass property, which is, sorry, a particle property, which is mass. Okay? So this relationship here shows the wave-particle duality of light. Okay? Copy that down, if you want. It's in the handle, but copy it down. When you finish, we have a small calculation to do. Right, so whenever question says find the Broglie wavelength, you have to take Planck's constant and divide it by its momentum, right? Mass by velocity. This is not c yet. This c is not speed of light. That c is the speed of the object, wherever it is. If it's light, well, it's speed of light. If it's a particle, it's speed of the particle. Okay? P is momentum. Momentum is mass by speed. Right? Just do me a favor, when you finish, try that calculation there for a minute. Find the wavelength of a ball of mass 500 grams moving with a speed of 20 meters per second. Find the wavelength of that ball and tell me what you notice about that ball. Tell me what you notice about that ball, right? Convert to kilograms, yes. Convert to kilograms. What you all got? How much? Minus 35. So how small the wavelength is. But the reason I gave you that is that a ball has a wavelength. So you're able to see that a particle could have wave properties. How can that ball have a more pronounced wavelength, a one that we could actually observe? What must happen? If I move faster, right? If it moves faster, you might be able to see a wavelength that we could actually observe. All right. All right. So 6.63 by 10 to the minus 35. And then if you do the reverse in number 2, you will see a much larger wavelength. Right? Like of an electron, so the wavelength getting larger. All right. So all these ideas that are very small particles, both particle and wave properties are important, and the particle energies are quantized, and what makes the quantum mechanics. We're not going into that. Right? So before we do Millikan, let's do a question on this, and we do. That's all to the book, right? Huh?
They got us Rogli's for a second.
Oh wait, no, that's one. Huh? Man. All right, let's run through this. We did all this already. Write an equation of energy in terms of photon and wavelength. Write that fast. What is that formula? What was that formula, Pete? Part 1. E is equal to H, no, the cell wavelength. HC and lambda. Nice. Write an equation for Einstein energy mass. What is that, Vishesh? Vinay. E is equal to MC squared. And then derive the Broglie. So what you have to do? Equate them, right? Do all of that, right? Lambda is what? I know, but tell me the formula for lambda. H on MC or H on P, right? H on P. So we did all that already, right? So I just running through that.
So,
Yeah.
in the exam, you have to do only look at.
Yeah. If they say derive, you have to show everything. If they say derive, you have to show everything. Try this, please, everybody. Calculate its de Broglie wavelength if they give you the electron 5 points.
Yeah, the first thing you have person.
Hurry up.
About the question.
Do I have something to?
All right.
I start reading. Okay. What's it?
Sorry. Kilovolt. Pete and Jacob, what do you think quick now?
Try.
Hurry up. Find the boy wavelength. Do we the boy? Alright, done? Right, what's the problem there earlier? They gave us what? 5.3 kilovolts. That's not useful. What we need? Can we convert? It's an electron, right? Can we convert that to joules? Something we can actually use? How we can do that? Remember? What's the formula? Energy is equal to what? E is equal to E is equal to, it have a V in it, have a Q in it. E is equal to Q by V. Right? You have the voltage and you have an electron. The charge is 1.6 by 10 to the minus 19. Find the energy and then find the wavelength in there.
Wait, so we can get the kilowatts.
Convert the volts. And then find the energy and then find lambda. Right? So you should have the energy value by now. That's 1.6 by 10 to the minus 19 by 5.3 by 10 to the 3. How much is that?
0.48 by 10 to the minus 16.
8.48 by 10 to the minus 16 joules. Right? And then we're going to use E is equal to HC on lambda. And we know what lambda is, right? Lambda is equal to HC on E. Plug it in now, tell me what you get for lambda.
So you got the last of this. But like I will do that, but
The 6.63 by 10 to the minus 34, right?
yes. Then minus 34. Like 2.35 by 34 minus 10. Phenomenal. So 2.35 by 10 minus 10.
Anybody else get up?
Yes,
2.35 by 10 to the,
minus 10.
right? So that's the value for the wavelength for that electron. Try the last part now. Calculate the frequency. Last part. Do that part said. Tiny, do one thing to the number. Two things. Oh, it's too much. Sorry.
Try.
So an oscillating molecule de-excites from one energy level to the next energy level, and the change in energy is that. Find the frequency. What's the formula we're going to use here? E is equal to, yeah, correct, HF. F is equal to E over H. But what's the problem there? What's the problem here with the E value? Is in what? Electron volts, right? How you go from electron volts to joules? How you go from electron volts to joules?
Not by 1.6 by 10.
Very good. So that'll be 2.2 by 1.6 by 10 to the minus 90. Work it out, that'll give you a frequency. How much all got there? 5.31 by 10 to the 4. All right, so that's it there.